Hi everybody, this is Andrew Wolf here, and in this video I'm going to talk about erythrocytes and hemoglobin. Now here I have an electron micrograph of a red blood cell and a platelet and a white blood cell. Sounds like the beginning of a bad joke, but I'm not going to go there. So you can see the red blood cell is a very smooth cell with what's called, and it's shaped like a biconcave disc. Biconcave meaning that if you look at it from a side cutaway, it is concave on both sides. Okay, and we'll talk about why that is in a second. This one here in the middle is a platelet, which is a cell fragment from pieces of a megalokaryocyte. And you can see it's got these little tendrils that stick out, and this tendril is there to grab things like von Willebrand factor or pieces of collagen from endothelial cells, and that triggers the platelet to sort of start clumping together. So these tendrils sort of grab onto those components, and the tendrils also grab onto each other so the platelets can clump together and form these big masses. And you can see this here is a white blood cell, and it is sort of peppered with these little tendrils, which are protein receptors. And so some of the protein receptors might be immune globulins or antibodies. Some of them might be MHC proteins, but there are just tons and tons of proteins on these white blood cells. Okay, so anyways, we're going to focus in this brief video on the erythrocytes, which is this biconcave disc. Now, what's interesting about this is you can see it has very few proteins on it, and it's very smooth. And this is because red blood cells, as being 45% blood, need to flow very smoothly. So the theory is that the biconcave disc and the smooth surface of the membrane allow it to flow very smoothly. So it is designed for good fluid or flow dynamics. Now also, the biconcave disc, if you just had a regular disc like this, you can see that it has less surface area than if it is a biconcave disc. So we have more surface area on the biconcave disc. So there are two advantages that we know about with the biconcave formation of red blood cells. One is that it improves flow through large arteries, and another is that it has a greater surface area, and that is very important because the more surface area there is, the more space there is for gases to diffuse in and out. So if we have oxygen diffusing in and CO2 diffusing out, the more surface area we have, the more efficiently that can happen. Now, interestingly, if you have, a red blood cell is usually about 7 nanometers wide. Now, some of the vessels in the body can be even thinner than that, and so the red blood cell actually has to sort of squeeze down to fit through. So it can't fit through as a biconcave disc. Now, when it gets out the other end and we expand into a large vein again, then the red blood cells can resume their normal shape. So they have what's called shape memory. And for those of you who remember or who have young children, you may remember the little silly bands that came out a few years ago, and they are these little rubber bands that came in shapes. And you might get a little dog silly band, and you put it around your wrist, and it gets around when it's stretched out, and then as soon as you take it off of your wrist, it bounces back into that dog shape. So that's just The exact same sort of phenomena occurs with red blood cells. They always spring back to their original red blood cell shape. So in a way, the erythrocyte was the original celly band. How does it do that? Well, the cell membrane, of course, just like every other cell membrane in our body, is made up of a phospholipid bilayer membrane, and it maintains its shape because of proteins within the cell. And the way that the proteins are aligned and the type of proteins they are is what makes it have that shape memory and always remember to spring back to a biconcave shape. Now, interestingly enough, there are some diseases like hereditary spherocytosis that is caused by mutations of these proteins within red blood cells, and they make it so that the red blood cells don't have shape memory and are not a biconcave disc, and they end up being spherical shaped, and it causes all sorts of problems, particularly actually with flow. They tend to not flow well in the red blood cell in the arteries and veins, and they break up into little pieces, and they also tend to get caught in the small microvessels, so it causes all sorts of problems. So now when we're talking, I'm going to look sort of, if you looked at this on the inside of the cell, you would notice that there is no nucleus. Mature red blood cells have no nucleus. A immature red blood cell, a reticulocyte, still has the nucleus, but before it completely matures, the nucleus dies. And it also has no mitochondria. In fact, it has no organelles at all. So there's no mitochondria. I didn't spell that right, but mitochondria. And that is really interesting because red blood cells cannot make use of oxygen. So even though red blood cells are carrying lots and lots of oxygen, they are only capable of anaerobic metabolism. Now, fortunately, red blood cells aren't highly metabolic cells, so they don't need a whole lot of energy. But the energy that they do need for just to keep the ion pumps running and things like that, they get from anaerobic metabolism. Well, why does it have no organelles or mitochondria? It's because the red blood cells are packed completely with hemoglobin. So the red blood cells sort of get rid of all of their organelles so that they can be completely packed with hemoglobin. And hemoglobin is, I believe, about 95% of all proteins in a red blood cell. And in a typical red blood cell, there are about 280 million hemoglobin molecules. Now, remember, there's 5 million red blood cells per ml. So if you multiply these two together in 1 ml of blood, you end up with, I think it's like 1 quadrillion hemoglobin molecules. Now each hemoglobin molecule in the red blood cell has 4 components. And inside each one there is a heme group, and each heme group can carry 1 oxygen molecule. But you can see, even though each hemoglobin molecule can carry 1 oxygen molecule, since we have a quadrillion hemoglobin molecules per ml, we can carry quite a lot of oxygen in our blood. Now, the hemoglobin is responsible for carrying about 97% of oxygen in our blood. The other 3% is carried dissolved in the plasma. Now, hemoglobin is loosely bound to the oxygen by what's called a hydrogen bond. And so actually the oxygen is sort of bouncing on and bouncing off of this. And the lower the partial pressure of oxygen inside the blood, the less is going to be bound to hemoglobin. So it's really dependent, the amount of oxygen that's bound to hemoglobin is really dependent on how much oxygen is dissolved in the blood surrounding that hemoglobin molecule. So as the amount of oxygen decreases in the plasma, more oxygen sort of falls off. Now, let me sort of give you a picture here. If you've ever seen the game Chinese checkers, you've got a whole bunch of marbles, and you kind of roll them around a plate that has holes on them. Some of the marbles are going to fall into these holes, and some are not. Alright, now the more marbles there are, the more likely it is that these holes are going to be filled. But as there are less and less marbles, these holes are less likely to have molecules to fill them. So this is kind of what's happening with hemoglobin. The oxygen is constantly, it's all surrounding these hemoglobin molecules, and it's constantly bouncing on and off, and then one bounces on, loosely connects to the hemoglobin molecule, and then a second later bounces off, and then a new one bounces on, and then that stays there for a second, and then that bounces off, and then a new one bounces on. So, and it really is dependent on the concentration of the oxygen around. The lower the oxygen concentration in the fluid around that hemoglobin, the fewer are going to be saturated, the fewer heme fragments are going to be saturated at any given time, the fewer hemoglobin receptors. Now what's interesting is there are a few conditions in the body that can change how the affinity of hemoglobin for oxygen. So basically, if you imagine this Chinese checkers game, there are things that make these holes bigger and easier to accept marbles. Big holes, the marbles are more likely to bounce into them. And then there are things that make the holes really tiny and it's hard for the molecules to bounce into them. So the big ones will accept oxygen molecules very easily. So they will tend to be saturated at a very high level. So you may have a hemoglobin oxygen saturation of 100%. But the big ones tend to hold on to oxygen very tightly as well. So that oxygen saturation is going to stay high even at the tissue level. It's not going to let go of the oxygen very well. These small ones, the oxygen molecules sort of barely balance on the outside lip. So it's going to have a lower saturation, but it's going to let go of them easier. It's looser binding. So what changes the nature of whether it's tight binding or looser binding? Well, it is due to a conformational change in the shape of the hemoglobin. And there are certain things that cause the hemoglobin to change shape. And these things are increased carbon dioxide concentrations, decreased pH, and a chemical called BPG. And it is this aspect of hemoglobin that causes shifts in the oxygen hemoglobin dissociation curve. And we're going to talk about that more when we get to the pulmonary section. So I just want you to be aware of the concept that there are two different conformations of hemoglobin, a tight binding conformation and a loose binding conformation. And it all has to do with changes, slight changes in shape of the hemoglobin molecule when they're exposed to one of these three chemicals in the bloodstream. Okay, so here we have our hemoglobin molecule, and you can see there's 4 binding sites for oxygen. Now also, each area here has a binding site for carbon dioxide as well. So hemoglobin also has the ability to bind with carbon dioxide. It is a different receptor than the oxygen receptor. So a hemoglobin can carry both an oxygen and a carbon dioxide at the same time. But interestingly, remember I said that increased CO2 causes looser binding with oxygen, and one of the reasons is when this receptor is carrying when the CO2 receptor is carrying a CO2 molecule, it loosens up the bond between the oxygen and the oxygen receptor on the hemoglobin molecule. Okay, so for functions of hemoglobin, what have we talked about so far? Well, we talked about carries oxygen, and now we just talked about how it can carry CO2. Now remember, it carries 97% of oxygen, but it only carries 23% of CO2. The rest of the CO2 is carried dissolved in blood, and even more significantly, by being changed to carbonic acid. Okay, and a third function of hemoglobin is to act as a buffer. And that's just because, like many amino acids and proteins within the body, it is a weak acid. And as you may remember from chemistry, weak acids and weak bases make good buffers. Okay, now the next thing I want to talk about is the iron cycle. And I want to talk about how the body reuses iron, and I need to start that with a discussion of the spleen. So the spleen is a large organ in the left upper quadrant of our abdomen that is fed by the splenic artery and drained by the splenic vein. Now, what's interesting here is this obviously branches off into small arteries and then small arterioles and then into capillaries. What we have here at the ends of the capillaries are these little spaces between the arterial circulation and the venous circulation, where the blood actually has to flow through the splenic tissue. And where it flows through there is an area called red pulp. Now the red pulp is tissue that is filled with macrophages. And so obviously there's an important immune role here, because the macrophages are going to engulf any pathogenic invaders, but another major role of these macrophages is to phagocytize senescent or deformed red blood cells, so old or deformed red blood cells. So the macrophages actually engulf inside the spleen, actually engulf these red blood cells and break them up into their component parts, which are primarily heme. Then it breaks the heme down. I'm sorry, it's primarily hemoglobin, but then it breaks the hemoglobin down into iron and bilirubin. Now, iron, being a heavy metal, is a cytotoxic chemical, and the body therefore has never lets it flow freely in the bloodstream in high quantities. So the vast majority of the iron in our blood is bound inside the red pulp, is bound to transferrin. So that's a protein carrier of iron. And so the iron plus transferrin is then transported through in the bloodstream to several different spots. It may be stored inside the red pulp of the spleen itself. It may be transported to the liver to be stored there, or it may be transferred to the bone marrow. And here apparently I'm assuming that this is a pediatric patient since I'm drawing a long bone. Now, if it's stored, if it's brought to either of these areas, the spleen or the liver, to be stored, iron is then changed into, is then bound to a different protein called ferritin. And this is the protein that is used for long-term storage of iron. Now, if the transferrin goes into the bone marrow, then it is ready to be used for the creation of new erythrocytes. So it is reconnected to a heme group and made into hemoglobin as part of a new erythrocyte. So the iron in the body is very tightly regulated, and very little of it is excreted. There is a small amount that is secreted through bile, but the vast majority of iron is recycled in the body. Okay, now the bilirubin is a breakdown product of hemoglobin that cannot be reused. So what happens with bilirubin after it is released by the macrophage inside the spleen is that it is bound to an albumin molecule, because bilirubin is not soluble in water. So it needs to be carried by an albumin molecule. This bilirubin coming out of the spleen is called unconjugated. So this unconjugated bilirubin is carried to the liver, and then in the liver, remember it's carried to the liver. So it's carried to the liver as carried by albumin as unconjugated bilirubin, and then the enzyme, there's an enzyme in the liver, and I won't get into the whole chemistry here, but an enzyme in the liver changes it to a conjugated bilirubin, and this conjugated bilirubin can be excreted through bile because it is now water soluble. So it's excreted with bile into the GI tract. So those of you who look at labs and look at things like if you have a patient with an elevated bilirubin level, then you need to decide whether it's elevated primarily because of unconjugated. So if it's an unconjugated hyperbilirubinemia, that would be due to increased lysis of red blood cells. the most common cause would be bleeding, like a GI bleed, because you've got red blood cells that are entering the GI tract and getting broken down, and then the products of those red blood cells are getting reabsorbed. If you have hyperbilirubinemia that is primarily conjugated, this has to do with a problem with the gallbladder. So we've got maybe a blockage here in the gallbladder, so bile is not being excreted, and the bile is backing up into the liver and getting absorbed into the bloodstream. So this is a problem with the gallbladder or liver. Okay, so that's why it's a good thing to really sort of understand how that bilirubin gets broken down and processed by the liver before excretion. Okay, that's it for this video. In the next video I will talk about the other cellular components of the blood, including granulocytes and lymphocytes. And if you want quick and easy access to the other videos within my Hematologic System channel, please click on this link here. Thank you very much.